Okay, so in the last video, we talked about the process of how to sample a signal. Okay, and we used impulse trains and we multiplied it by our original signal, and then we got the sampled version. What we're going to talk about today is recovery after sampling. Okay, we're going to talk about recovery after sampling. Recovery after sampling. Okay, so let me just remind you of the setup here. So let's say I have, my arbitrary signal x of t. And remember, we wanted to look at it at these locations. Okay, so those were going to be our samples. And what we did was we multiplied x of t by an impulse train, and we ended up with our sampled signal. And what did it have? It had all these delta functions whose heights or areas were given by the values of our original x of t at those locations that we're sampling at. Okay, remember we had this thing called the sampling period, right? 2 t sub s and so on. Okay, and so this was our sampled signal. And you can see that it seems like we've lost a lot of our original signal, and we have, right? Our new signal here, our sampled signal is 0 in all these in-between spots, right? But our x of t is not. It's got this whole curve going through it, right? So the question is, can we actually go from just this sampled signal and recover our original signal x of t exactly? Okay, can we go backwards? Can you take the sampled signal and find a way to fill in everything in between here in order to get back to x of t exactly, not an approximation, actually exactly for every single t? And your first guess might be to, maybe connect the lines here with straight lines, but clearly that's not right, right? Because we have curves here. Okay, we have curves there. Okay, so it's a little complicated. Uh, if you're just looking at it for the first time, it seems really complicated. How could we possibly fill in between all those samples? Turns out it's actually not so complicated, and we're going to do that today. And there are going to be certain conditions under which this is possible. Okay, but for now, we're just asking the question, can we recover all of x of t from knowing just the sampled version? Okay, and it turns out under certain conditions, okay, the answer is yes. And those conditions are going to be pretty general, actually. It's not too restrictive. Okay, so it turns out this is possible, and really you're doing it all the time, every day, whether you're talking about your computer or your cell phone or anything. Anything that's digital, okay, cannot be a continuous time waveform, right? Because continuous time, there's too many t values here. I can't store x of t for every t value. So whenever you're working digitally, digital signal processing, you're working with sampled signals. But then when you want to go, let's say you're working with audio, for example, and when you want to hear the audio back through a speaker, speakers are analog devices, right? They have a diaphragm that's moving in and out, pushing air toward your ear. Okay, so that is a continuous time signal. So anytime you're working with something on the computer and then you want to hear it out of a speaker, this process is happening. We're going back, we're recovering the original signal, or maybe you've made some changes, but we're going from the samples to the correct continuous time signal. Okay, so this happens all the time, right? Even listening to this video right now, it's happening. Okay, so this is what we're going to look at mathematically in this video. So just so that we can get ourselves organized, let me draw a sampling block diagram. Okay, that's kind of a summary of what we're going to do. So last video, we started with x of t, and we multiplied it. Okay, this is just a block diagram symbol for multiplication, just a circle with an x. We multiplied it by an impulse train. Okay, so delta of t minus nt sub s. Okay, this is an impulse train, of course. All right, and remember, we also had the sampling frequency, which is 2 pi over the sampling period. So the sampling period appears right there in the impulse train. We're also going to use the sampling frequency. And then what did we get out of that multiplication? We got our sampled signal, right? Our sampled signal x sub s of t was just x of t times our impulse train s of t. So what's the plan now? Okay, what are we going to do? Well, we want to devise an LTI system so that when I put my sampled signal in, I'm going to get out some output. I'll call it y of t. And hopefully, as long as I make sure certain conditions are true, I would love this y of t to actually equal my original signal, x of t. I want to show with this block diagram that we can sample our signal and then eventually put it through an LTI system, and as our output actually recover x of t from the sampled signal. Okay, so there are going to be certain times when this output equals our original signal, in which case we get recovery, okay, of our original signal from the sampled version. But under other conditions, maybe this output doesn't equal the input, in which case something went wrong, okay, and we didn't recover. So we're going to see in this video exactly the conditions we need to ensure perfect recovery. Okay, so let me just write down kind of what I just said. So we want to find an LTI system as shown above. Okay, such that the output y of t actually equals x of t, and this is of course for all t, okay? So for all t. So I'm going, again, it's a crazy thing that we're going to be able to do this, okay? But just from these samples, I want to be able to somehow pass it through an LTI system and recover this input signal exactly. That's my goal. Okay, and what's the plan? The plan is to use the frequency domain, actually. Okay, we want to use the frequency domain and try to make y of omega equal x of omega. Because of course, if the Fourier transforms are equal, then the time signals are also equal. Okay, so I'll just write that, which is equivalent to y of t equals x of t. And that's just after taking inverse Fourier transforms, of course. Okay, so that's our plan. We want to take y of omega and somehow create x of omega out of it by passing it through an LTI system. And then, of course, from that, taking inverse Fourier transforms, we would get what we wanted, that y of t equals x of t. Okay, so let's first consider when x of t is what? Band limited. And this is something we had a whole video on. And here's where it comes up. So let's first consider when x of t is band limited. Let me just remind you what that definition is. That means there exists some max frequency omega sub m such that our x of omega signal equals 0 whenever the absolute value of omega is greater than omega sub m. Okay, so remember that means I can put kind of these bars at plus or minus omega sub m on my x of omega signal, and the signal is 0 outside of that. So just so we have something to look at, this is going to be our kind of picture example throughout this video. So I'm just going to use a triangle that goes from negative omega sub m to omega sub m. Call this x of omega. And again, we're just going to use this as an example. Okay, so we're just going to take that picture as an example. Of course, it doesn't have to look exactly like that, just the triangle's easy to draw, essentially. So that's what we're going to use. And so let's think about what's happening in the frequency domain. We want to understand this function in the frequency domain, and that's the output from this function in the frequency domain. So first, let's look at the sampled signal in the frequency domain, and we did that in the previous video. We saw in the previous video that the Fourier transform of that sampled signal is actually pretty simple. Remember, it's just a big sum of scaled shifted copies of the original x of omega signal. Okay, we saw that in the previous video, so let me draw that. What does that look like? Looks something like this. Okay, so we're going to have a copy centered at 0, and we're going to have a copy centered at omega sub s. Right, just all the integer multiples of omega sub s. Negative omega sub s, negative 2 omega sub s, and so on, dot, dot, dot. And the height is scaled by 1 over t sub s. So it started out as 1, multiplied by 1 over t sub s. That's what we get. Okay, and this is negative omega sub m. That's omega sub m. Okay, and this point right there is going to be important to us. And this is, of course, omega sub s. And then I'm just subtracting omega sub m, right? Just going to the left by omega sub m, this distance, but just shift it up here. Okay, so as I've drawn it, you can see that these triangles don't overlap with each other. They don't interfere with each other at all. It turns out that's going to be an important thing for us. Okay, we don't want these triangles to interfere with each other in the frequency domain. So let's look at the condition that would make that true. So there is no overlap. In other words, interference. Interference between these copies of x of omega on the omega axis, provided what has to be true. Well, look, I just need there to be a little gap there, right? As long as there's a little gap there, that next copy of the triangle is pushed over far enough so that the triangles don't overlap. And on the left-hand side, it's kind of just the same thing, kind of the mirror image, right? This point right there is negative omega sub s plus omega max. If we have a little gap there, we're also going to have a little gap here based on the example we're looking at. So let's just focus on this right side. Okay, so we need there to be a little gap right there. And what does that mean? That just means we need the max frequency here, omega sub m, to be less than omega sub s minus omega sub m. Okay, just multiplying both sides by -1, just really quickly, just to show you. We get this condition, which is exactly the same on the other side. Right, that this is to the left of this. That means there's a gap there. It's the same condition as we had for this side. So that's what I was saying before. It's just kind of a symmetric case for this example. So we're just going to look at the right side for now. And that's all we need. Okay, as long as there's a gap here, then by what I just said, there's going to be a gap over here. There's going to be a gap everywhere. Okay, so these triangles are completely separated from each other, provided this is true. This condition is true. You can just see it looking at the picture. And we're going to slightly rearrange that, bring the omega m to the left side. And this says 2 omega sub m is less than our sampling frequency. Okay, so as long as 2 times the maximum frequency is less than the sampling frequency, we're going to get this gap between our triangles, which is going to be useful for us. And we'll come back to this condition a little later. So what is this saying? This is just saying the sampling frequency is at least twice the highest frequency in x of t. Okay, that was our omega sub m. All right, so now as long as we have that condition and we have these triangles separated, what's the end goal? Well, the end goal, remember, is I want to have my output y of omega equal my input x of omega. So I want my output to equal this x of omega. And remember, the output is what I get after passing it through some LTI system. We want to design that LTI system right now. So if I'm given the Fourier transform x sub s of omega, I want my output Fourier transform to just equal x of omega. What can I do? Well, look, if I'm given this, how can I create this out of it? Well, I just want to get rid of all of these extra copies, just be left with this perfect one, and then just scale it by t sub s to make the height work out, and that would be exactly my x of omega signal. Okay, so that's what I want to do. What we're going to do is put a low pass filter on this signal to get rid of all of these high frequency components and just be left with our perfect copy of x of omega, and we'll scale it appropriately to get back exactly x of omega. So let's do that. So now we can use a low pass filter to obtain x of omega. Okay, and what should our filter be? Well, it's pretty much what I just said. Okay, so we want it to be a low pass filter. Okay, and I'm going to label this as omega sub c and negative omega sub c. Those are called cutoff frequencies, which I'll write down in a second. And what's going to happen is it's going to look something like this, and we just want to make sure that the height is t sub s, so that when I multiply it by the height there, 1 over t sub s, I get back to the height 1, which is what I want. Okay. I'm going to make this height t sub s. And I'll draw everything in 1 second. Let me just write that plus or minus omega sub c are the cutoff frequencies. So just some terminology you'll hear. Cutoff frequencies of the low pass filter. Okay, and what should we make those cutoff frequencies? Well, from the picture above, you want what? Well, we just want to make sure that that right-hand side of this low pass filter falls in this gap, right? That's part of the reason why we wanted to have a gap there, so that I can make the right-hand side of my low pass filter fall somewhere in there. So what do I need? I just need this omega sub c to be between omega m and this, omega sub s minus omega m. That's it. That would mean that right-hand side would fall in here. And again, by that sort of symmetry argument, that means the left-hand side would fall in between here as well. Okay. So what do we want? Well, it's just what I just said. We just want omega sub m to be less than omega sub c, less than omega sub s minus omega m. Okay, we just want to make sure the right-hand side falls somewhere in there. Okay. All right, so that's good. So now we want to actually analyze what this output is. We already kind of saw it drawn out, but let's do it in depth. So our situation is that we have our sampled signal going into this LTI system with this frequency response. And what we're getting out is our output y of t. That's just this part of the block diagram. Okay, that's all that's happening. And so what does that mean for y of omega, the Fourier transform? Well, we've seen this before. This just means the output Fourier transform is just the input Fourier transform times our frequency response. And again, based on the picture, right? If I put this low pass filter here with height t sub s, what's going to happen? It's going to zero out all of this stuff. Okay. I'm just going to be left with this triangle. It had height 1 over t sub s. So when I multiply it by t sub s, the frequency response, I get back to height 1, and that is exactly my x of omega. Okay, so hopefully just from that picture, you can see that this is going to be our x of omega. Okay, and I'll just draw it here. We get back exactly this one triangle. This is y of omega equals x of omega, omega sub m, negative omega sub m, height 1, and the frequency domain. Okay, so let's just review what do we actually have here. Well, this is a perfect reconstruction of x of omega. And so what do we get from this? Just taking inverse Fourier transforms, the output y of t, after putting our sampled signal through this LTI system, actually equals our original signal, x of t, exactly. Triple exclamation point. Okay, this is insane. This is really crazy and very interesting and cool that this is possible. That we could go from this sampled signal, okay, just these samples, okay, just these delta functions, put it through this very simple LTI system, just a certain low pass filter, and the thing that we get out, y of t, is exactly our x of t. So somehow this process figures out exactly how to fill in between these sample points to get back our x of t perfectly. Okay, really, really cool stuff. Okay, and this is mathematically why it's true. All right. So great. So now, let me just say one more thing, just some more terminology. That H of omega is actually given a name sometimes. It's called a reconstruction filter. And it is an ideal low-pass filter. Okay, so we are using an ideal low-pass filter, meaning we can have these sharp cutoffs and it's got a perfectly flat height, right? Things like that. So in the real world, we can't create these ideal filters. And so there are some, approximations and different things that are done in the real world to try and have this be as exact of a recovery as possible. Okay, but for us in our idealized math world, we actually get perfect exact recovery using this ideal low pass filter. All right, so I want to go back to one of those conditions we saw. So we have seen that if our sampling frequency is at least twice the max frequency, right? We saw that right here. So if we have that condition, then these triangles are spread far apart enough that we can fit a low pass filter in and extract one perfect copy of our original Fourier transform. Okay, so if we have this condition, we've seen then perfect reconstruction perfect reconstruction of x of t from its sampled signal x of s of t is possible. And it turns out this statement has a name. Okay, this is the Nyquist theorem. Okay, that if my sampling frequency is at least twice the max frequency, then perfect reconstruction is possible. That's the Nyquist theorem. And 2 omega sub m is given a name. That frequency is called the Nyquist sampling frequency. Okay, so just some terminology you might hear. Okay, so where does this show up in the real world? Well, if you are familiar with CDs, audio CDs, it turns out the sampling rate for CDs, a CD is a digital medium. Okay, so what's stored on there is not the continuous waveform of audio, but a sampled version. And the sampling rate is 44.1 kilohertz. And so using this Nyquist theorem, okay, if this is the sampling frequency, then what could be the max frequency of my signal? We'll just bring 2 to the other side. The max frequency of my audio signal can be at most half of that, which is 22.1 kilohertz. And you can see now why that sampling frequency was chosen, because human hearing only goes up to around 20 kilohertz. So when they designed the CD quality audio standard to have a sampling rate of 44.1 kilohertz, they had this theorem in mind, because that would ensure that you could represent in your audio frequencies all the way up to 22.1. Your max frequency can go all the way up to there, which is beyond the scope of human hearing. And so they figured that anything that humans would be listening to, this was more than sufficient. Okay, this was more than sufficient to make sure that you can get perfect recovery for any audio that had max frequency at most this. Okay, so that's kind of a real world example of where this Nyquist theorem comes into play. Okay, so this is all great. And I wanted this first example to be a case where we could get perfect recovery. And so I put some conditions on our signals. Okay, and one of them was the band limitedness, which we're going to come back to later. And the other one is this Nyquist condition. So what happens if that's actually not true? What goes wrong? So what happens in this example if we actually sample less than 2 times the max frequency? Okay, sometimes this is called undersampling. Okay, so we're not sampling fast enough. Okay, in other words, what happens if we violate this Nyquist condition in this example? Well, here's what happens. I'm going to draw it here. And I'm just going to first draw all of the different shifted copies. I'll draw it in red. This is not the actual function. Okay, I'm just drawing all the shifted copies, and then we have to add up those shifted copies, of course. Right? We have to add up all the shifted copies. Right now, I'm just going to draw them all, and then we'll look at what they might look like added up in a second. So if I draw them all, I'm just going to get all of these shifted copies like this. Okay, dot, dot, dot. Same on the other side. Okay, and let me label these places. So these are definitely located at integer multiples of the sampling frequency, but now the sampling frequency is smaller, right? And so in this picture, the sampling frequency isn't so large, it's smaller. So these copies are getting squished together, and they're getting squished together so much that we actually get overlap here, right? There's my omega sub m. Okay, there's my omega sub s. And it turns out there's a name for this overlap. So this overlap is the issue, because then when I add these triangles up, they're going to interfere with each other there. And we give this overlap a name. So this overlap between copies of x of omega is called, this is a term you'll hear, it's called aliasing. Okay, and it's an issue for recovery because after I add all of these red signals up, right, these were all the shifted copies, they all have height 1 over t sub s. Now I have to add these all up to actually get y of omega. So after adding all of the red copies up, we get something like this. Okay, so what would it look like? Well, this is, again, just a sketch, right? Not saying it's exactly this, but you can see I'm going to get kind of this peak from the first one, right? And then I have to add up these two signals here, and they're both kind of sloping down linearly. Probably when they add, they'll give me something sort of like a flat line there. So I'm just going to draw it like that, maybe something like this. That's what I get. Then the next peak, then the two parts where they add, where they interfere, the aliasing area. Okay, and this is sort of what we're going to get, something like this, once I add them all up. Okay, and this is an issue for trying to recover, right? How could I put a low-pass filter on this signal and get back my triangle? I can't. If I were to put a low-pass filter, maybe like something like that, what I would end up with is not a triangle. What I would end up with is something that looks like that. That's not my original x of omega, right? There's been interference in these parts. The aliasing has made these copies of the original x of omega interfere with each other. And now I can't use a low-pass filter, or really any LTI system. I mean, these copies of triangles have just interfered with each other. I can't undo that interference, right? So there's nothing I can do. Okay, I can't recover in this case. So this is what goes wrong if we undersample. Let me just write that. There's no way, maybe I'll write in general, to obtain a perfect copy of x of omega from this y of omega. Okay, and I'll just write there is aliasing. So the copies have interfered with each other. Yeah, I don't see a perfect copy of my triangle there, so I can't extract that from this y of omega anymore. Okay, so that's what goes wrong in this example if we undersample. But if you remember, there was one more condition I put on my original x of omega. It was at the very beginning. And that was that x of t was band limited. In other words, there exists some max frequency in my signal, after which my x of omega is just 0. Okay, so you might ask yourself, well, is that really a strict condition? And the answer is no. I mean, just think about audio for an example, right? Humans can't hear past 20 kilohertz. So certainly whether your original signal has frequencies larger than that or not, you can just artificially get rid of them and make your signal band limited if it isn't already, and you're not going to change anything, right? Humans can't hear past 20 kilohertz. And so you might as well just artificially, if you have to, band limit your signal to get rid of those frequencies because no one can hear them anyway. Okay, so for audio, this is certainly not a difficult assumption to ensure in real life. And it turns out in general, almost all signals are either band limited or can be made so, right? Just by sort of after a certain point, if your x of omega is not actually zero, it's probably going to be extremely small and you might as well make it zero. So this band limited assumption is not a big deal. Pretty much everything we want in the real world, like I said, is either band limited or can be very closely approximated as such. And so it's a perfectly fine and general assumption to put on this entire sampling discussion. But let's just see what does go wrong if our signal is not band limited, just to get a picture in our head. So what if x of omega is not band limited? Okay, so again, just to have something to look at, let's just say it looks something like this, right? Maybe it's sort of like a decaying exponential on both sides. Maybe this is my x of omega. Okay, so it never quite reaches zero. It's not band limited. There's no bars I can put on it and have it be zero outside of it. There's always going to be non-zero stuff. Okay, so what would our y of omega look like when we add up a bunch of these shifted copies? Again, I'm just going to draw all the copies. I don't want to add them all up because it could get complicated, but it's going to look something like this. Right, all these shifted copies that are centered on integer multiples of omega sub s, the sampling frequency. This is zero, this would be omega sub s, this is like negative omega sub s, and so on. Okay, and clearly, because we don't have the band limited assumption, these copies are always going to interfere. There's always going to be aliasing. I can't spread these copies far enough apart to have them never interfere with each other because they're never zero after a certain point, right? There's no point after which they're never zero, I guess I should say. They always have non-zero values stretching in both directions forever. So there's no amount I can shift by to get these copies of x of omega to not overlap and interfere with each other. Okay, so there is no amount we can shift by. We can shift these copies of x of omega by to have them not interfere with each other. Okay, they're always going to have their tails interfering with the other neighboring copies. And I can put this another way. In other words, we cannot sample fast enough, right? We cannot make the sampling frequency large enough. We can't push it far enough to the right to have these copies interfere with each other. We can't sample fast enough in order to ensure perfect recovery of x of t. Okay, because these x of omegas never eventually equal zero. I can't push them far enough apart from each other so that they don't overlap with each other, so there's no aliasing, so that I can extract one perfect copy. There's no way because x of omega is not band limited. Okay, so that's what goes wrong if x of omega is not band limited. So now we've seen the good case, what happens when Nyquist is violated, the Nyquist condition. We saw what happens there. We get aliasing. Now we saw what happens when the signal's not band limited. Okay, so we've kind of seen all the different cases of what can happen with recovery after sampling. So let me just summarize the good case. So in summary, if, and now I'm going to write the conditions to ensure that we can recover x of t exactly. Okay, so first of all, we need x of t to be band limited. We've seen that now. We've seen why. X of t is band limited with maximum frequency, say some omega sub m. Okay, that's one thing we need. Now we need Nyquist. We need to sample fast enough. We have to make sure the sampling frequency is large enough. We have to make sure we don't undersample. We need the sampling frequency to be at least twice that max frequency. Okay, this is the Nyquist theorem. Okay, we need to use the reconstruction filter, low pass filter. Let me just remind you what it was. Looked like this. So it had height T sub S, and it had these cutoff frequencies plus or minus omega sub C. Okay, we have to use that low pass filter. Okay, with what's the condition? Well, we just need that cutoff frequency to fall between those copies of x of omega, if you remember. And that condition we already saw was omega sub m is less than that cutoff frequency, less than the sampling frequency minus omega sub m. That's just saying that cutoff frequency is between the copies. So we can extract our perfect copy of x of omega. So if these three conditions are true, then we can recover x of t from its sampled version. Exactly. Pretty amazing. Okay, pretty amazing. So that is the story of recovering our signal after we sample it. Okay, we've gone through and seen the good conditions that I've summarized here and also what goes wrong if they're not true. Okay, and so hopefully this really makes sense to you and you can now understand what's happening in your computer and your cell phone or anywhere where an analog signal like voice, for instance, is converted into the digital domain it's sampled and then recovered eventually after from the sampled version in order to be put through speakers, which is an analog medium, so that we can hear it in real life. Okay, so great. So that was this video. That's all I had for this video, and I'll see you in the next one.